Alright, so today we're talking about matrices. Specifically, we're talking about matrix multiplication. So we first start off with what exactly is a matrix. And so a matrix is essentially going to be a lattice of numbers composed in rows and columns. And so we might have, for example, a matrix that might look something like this, and that would be a 2 by 2 matrix because it's composed of 2 rows and 2 columns. So let me write that down. 2 rows and 2 columns. 2 by 2. 2x2. And that, for example, might be denoted by matrix A. We use capital letters here to denote each of the matrices. You might also have, for example, another matrix, matrix B. And this time, this same matrix could have, 3 columns and like 2 rows. So we might have, because we ended off with D, we might have E, F, G, H, I, J, like that. And once again, it has 2 rows and 3 columns. And so let me write that down. So we have 2 rows and 3 columns. All right, so we have a 2 by 2 matrix. We have a 2 by 3 matrix over here. So what's the idea behind multiplying these matrices, right? We might introduce the idea of multiplication of matrices. Multiplication. And so the idea is that we might have A times B, and that could be any matrix C. And this is possible for us as long as the number of the number of columns in matrix A is equivalent to the number of rows in matrix B. So let me highlight that actually. So the number of rows or columns in matrix A must be equal to the number of rows in matrix B. And so as long as these two are equivalent to each other, then we can multiply them. And the process of matrix multiplication, I'll go through that in the next few moments. But the idea is that looking at the dimensions of both of these matrices, we should be able to make a judgment as to whether we can multiply them together. And so as such, when we're asked whether or not we can multiply, B times A, for example, well then, that's not possible. This example here is not possible. And that's simply because if we were to do that, then the number of columns in matrix B, does not match the number of rows in matrix A. And so while A times B might be possible, matrix multiplication wise, B times A would not be possible. And so this idea of the cumulative property does not really apply to matrix multiplication 100% of the time. Now there's also the idea of scalar multiplication. Scalar multiplication will not be explained in this video, but it's pretty intuitive. You can multiply any given number by all the values in the matrix, and that is why it's referred to as kind of a scalar, because we are applying it at scale to all the values. So let's look at an example problem to actually talk about the process of matrix multiplication itself. Alright, so we're asked to find A times B and B times A if either of them are possible. Well, looking at the dimensions of our two matrices that we have here, A and B, let me bring out the marker real quick. So we have we have 2 rows and 2 columns in this matrix over here. 2 rows and 2 columns, pretty self-explanatory. We also have 2 rows and 3 columns in this matrix over here. So let's see what operations are possible. We have A times B, which is definitely possible because it is a 2 by 2 matrix, we have 2 columns and 2 rows, and respectively in both matrix A and B, and so that is possible. They're equivalent to each other. But let's say if we flip the script and we do matrix B times matrix A, well, that is not possible because these two are not equivalent with each other. We have 3 columns in matrix B and 2 rows in matrix A. They're not equivalent with each other, and thus it is not possible. One thing I would like to note, though, that our resulting matrix between the multiplication of A times B will result in a 2 by 3 matrix. And that is not by coincidence. That is because there are 2 rows in matrix A and 3 columns in matrix B. And so you can think of the dimensions of our resulting matrix to be defined by the outer dimensions of the 2 by 2 and the 2 by 3, and the inner dimensions determine whether or not that's possible. But I digress. So now we're going to talk about how we're actually going to multiply these matrices. How we're going to actually multiply these matrices. And so what we need to really think of this is that we're multiplying, when we do A times B, when we're doing A times B, we're multiplying the row of matrix A by the columns of matrix B. And so let me look at that. Let's look at that in practice. We need to treat each of these as kind of vectors. And when we're talking about each of these as vectors, we're talking about each row and each column we're treating as a vector. And so let me explain that. So we first start off with this first row in matrix A and this first column in matrix B over here. Let me highlight those actually. So we have this first row over here, matrix A, and this first column in matrix B. And so that is composed, if you just look at those singularly, that's basically just a vector. It's just a 3 and 4, and then we also have 5 and -6. And we're asked to essentially find the dot product between both of these vectors. And the dot product, if you'll remember, is just 3 times 5 plus 4 times -6. Now, you might not be completely familiar with the dot product, especially if you're taking a pre-calc course, but you can simply imagine it as we're taking these first two values over here, these first two values, and then we're going to multiply them with each other, and we're taking these two second values over here, and we're multiplying them with each other. And so hence comes the idea of a dot product, and that is what we're basically doing here when we're multiplying these two matrices as well. We're treating these rows and columns as vectors. We're finding the dot product, and using the formula that we have outlined, we will find a specific value in our matrix. Let's do it with the second column and still the first row of matrix A, because we're still on the first row of matrix A. So what we have here is we are continuing on. We have 3 by 4 multiplied by now we have actually 2, 0 over here. So we have 2, 0, and so that is what we are going to be using. 3 times 2 plus 4 times 0. We're going to add those together. We're going to evaluate all of these all in one go, but for now I'm just going to write down the expression. Next we have this first row of matrix A times the first column of, or third column of matrix B, and so that is again going to be 3 and 4 multiplied by the vector -8, 9. Again, 3 times -8 plus 4 times 9. You see the pattern here, right? We have the first row of matrix A. We first start off with that. We're finding the dot product with respect to each of the columns in matrix B. And then we're now going to move on to the second row of matrix A. So let's move on to the second row. And so for the second row, we have -7 and 1. -7 and 1. So let me do that in a different color. -7 and 1 over here. And we're using this, we're just going to loop through each of the columns in matrix B just as before, actually. And so actually I will bring this over just so that, actually we don't need all of that. We just need these vectors over here. But we are bringing these down, and then we're going to find the dot products for each of these columns with respect to the row that we already have defined above, and that row is going to be -7, 1. And so we are finding dot product with respect to the vector -7, 1. And so what that's going to look like in practice is we are multiplying each of the first values by the second values and adding them together, both of those products together. Alright, so we have -7 times 5, -7 times 2, -7 times -8. Those values are going to be added with their respective second values, which are 1 over 1 -6, 1 0. Whoops, I'm writing this incorrectly. 1 -6, 1 0, and 1 9. All right. So essentially, what we have here is we have a number of expressions that can be evaluated that can determine the values of our resulting matrix after being multiplied, after A is multiplied by B. So let's first evaluate these. So we have 3 times 5, which is 15, plus 4 times negative 6, which is negative 24. So 15 minus 24 is negative 9. All right. Next, we have 3 times 2 plus 4 times 0. 4 times 0 is 0. 3 times 2 is 6. So the resulting value is 6. Next, we have, let me bring this down here actually. Next, we have 3 times negative 8, which is negative 24, plus 36, because 4 times 9 is 36. So 36 minus 24 is going to be 12. Negative 7 times 5 is 35, minus 6. That's going to be negative 41, actually. Then we have, again, we have a 0 over here. This value is going to be completely 0. Negative 7 times 2 is negative 14. Once again, we're going down, and our last expression to be evaluated is going to be negative 7 times negative 8, which is going to be 56, plus 9 is going to be 65. And so what we're left with is negative 9, 6, 12, negative 41, negative 14, 65. So let me actually take these values over here. Let me go up, take all of these values. Whoops. Okay. And I'm going to copy them, and we're going to bring them down over here. And now we know from the fact that we are multiplying a 2 by 2 matrix by a 2 by 3 matrix. And so because we know that we're multiplying a 2 by 2 by a 2 by 3, we know again that the resulting matrix is going to be a 2 by 3 matrix. And how do we know that? Again, well, we have 2 by 2 multiplied by a 2 by 3. We're using the outer dimensions over here, and so we have essentially a 2 by 3 matrix that we're going to call C. And so C, which is going to be A times B, so A times B, which is going to be equal to C, well, they're going to be, the values in C are going to be the values that we have in front of us. But how are we going to arrange those values? Well, we know that it has 2 rows and 3 columns, and so the 3 columns, each column is going to be composed of respective values, and we're going to go like this. We're going to go, okay, so this is going to be in row 1, column 1, row 1, column 2, row 1, column 3, and now we move on to the next row. So this is going to be row 2, column 1, row 2, column 2, and row 2, column 3. And so, thus composing our matrix, we have negative 9, 6, 12, then we have negative 41, negative 14, and 65. And that is how you multiply matrices. Let me just go through this process once more just to explain what we did. We treated each of the rows in matrix A and the columns in matrix B as vectors. We found the dot product of these vectors by taking the first component and the second component, multiplying those respective components together, and adding up the products. In doing so, we have essentially a number of values to be arranged into a matrix. We know the dimensions of the resulting matrix is going to be a 2 by 3 because we know the outer dimensions of our 2 multiplying matrices. And so knowing the dimensions and knowing the values, we can arrange them in a 2 by 3 matrix, and that resulting matrix is as follows. And so it's a pretty complicated process, seemingly. And many calculators actually do this automatically, but once you get the hang of it, you can actually do it by hand pretty easily. Let's look at a word problem of what these kind of questions might actually look like. All right. We are told that different point values are awarded for different shots in basketball. Use the information to determine the total amount of points scored by each player. And we have the players Ray, Chris, and Jerry. And we are given the number of free throws, 2-pointers, and 3-pointers were scored by each of our players. And we also have the point values that are denoted for each of our shots. All right, so first of all, we can very clearly see that these are supposed to be arranged in a matrix. And by arranging these values into a matrix, we can multiply them together, and we will get a resulting result that will actually show us the total amount of points scored by each of the players in order. And so what we first need to do is determine in what order we're going to have these matrices being multiplied into. So we have a matrix A here, and the dimensions of matrix A can be defined by 3 by 3. It has 3 rows, 1, 2, 3, and 3 columns over here. We also have matrix B. Dimensions of matrix B are going to be equivalent to what we have 3 rows over here and 1 column over here. So it would be beneficial for us to probably multiply the matrix A first by matrix B, and then our resulting matrix will be a 3 by 1 matrix, and so it will have 3 rows composed of each of the players' point totals as a singular value. All right, so let's do this. Let's do the matrix multiplication. So let me erase this real quick. Whoops. Okay. So first, let's compose our matrices. We're first going to we don't even need to compose the matrices. Let's just do the dot products. And so first, we're going to multiply the values in this row by the respective point totals. And so again, we're treating each of these as vectors. And so what we're going to have is 44, 32, 25, and that's going to be for Ray. The point totals are 1, 2, 3, and that's going to be equivalent to 44 plus 32 times 2 is going to be 64, plus 25 times 3 is 75. All right, moving on, we're going immediately now to the second row and second row, and we're still on the first column here of our second matrix. And so let me use a different color. So we are doing this dot product of the point values, and so what we're going to have is 37, 24, 31 dot product 1, 2, 3. 37 times 1 is 37, plus 24 times 2, which is 48, plus 31 times 3 is 93. All right, moving on to the last row of our first matrix. What we're going to have is this row of values being multiplied again by 1, 2, and 3. And so what that leaves us with 35, 39, 29, dot product 1, 2, 3. That's going to be equal to 35 times 1, which is just 35, plus 39 times 2, which is going to be 78, plus 29 times 3, which is the same thing as 90 minus 3, which is equivalent to 87. Yeah, okay, so we have each of these expressions, which we can now evaluate. 44 plus 64 is the same thing as 108. 108 plus 75 is going to be 183. All right, next we have 37 plus 48, which is going to be the same thing as 85. 85 plus 93 is 178. 85 plus 93, 178. Okay, finally we have 78 plus 87, which is the same thing as 165. 165 plus 35 is going to be 200. All right, and so thus we have our point totals. The resulting matrix is a 3 by 1, which we talked about earlier. And so thus, the point values are essentially going to correspond to each of the rows we have here. So we have Ray, Chris, and Jerry. So Ray is going to have scored 183 points. 183 points. Chris, I believe, is going to have scored 178 points. And Jerry is going to have scored 200 points. So Jerry scored the most points. All right, and that is it. That is the answer to our problem. I'll be posting the PDF version of these notes on the description of the video. Thank you so much for watching. If you have any questions, please feel free to leave them in the comments, and I'll try to get to them. Otherwise, thank you very much, and yeah.